My name is Christopher Kelly. I work for Wallbridge on the Fenelon project up in northern Quebec. And I'm just going to talk to you about photogrammetry and how we used it during our bulk sample. Just a quick cautionary statement. So there might be some forward-looking statements in this presentation. I'm not going to go into detail on this. So a bit of a background on Wallbridge Mining as a company. So we're a Sudbury-based exploration and mining company with projects both in the Sudbury Basin focused on nickel copper PGMs, as well as gold projects up in the Abitibi Greenstone Belt. For the last few years, our main focus has been on the Fenelon deposit up in northern Quebec, where we completed a bulk sample in 2018 and 2019. So I'm just going to jump right into it. So for those of you who are not familiar with it, photogrammetry is the process of making 3D photorealistic meshes using a collage of 2D photographs. So we take the photographs of the face just using a standard digital single lens reflex camera, and then we use a third-party software to stitch these into the 3D mesh that applies the colors onto them. So we are able to use this in Leapfrog as a base for modeling, structural data collection, and even can be used for stope design and interpretation of fracture sets in geology. Kind of what I think is one of the most powerful uses of these is that they serve as a permanent record and an unbiased record of the rock. And this is quite useful when you have new people coming into a project. You can reevaluate the geology. So initially, this was brought into mining by Richard Knight at the Balmat Zinc Mine in New York State. He has a paper that he published in 2017 that outlines how they used photogrammetry to help model, as well as to perform the grade estimations and do reconciliation at the mine. So these photos just show some of the detail that can be collected from these photogrammetry meshes. So in the bottom right is just the outline of the ore deposit shown in red, as well as some internal folding that was outlined in purple. In his paper, he kind of outlines the effectiveness of the photogrammetry in geometrically complex deposits. And really, the beautiful thing about this is that the geologist can spend the time at the face collecting crucial and critical geologic data and not spend the time trying to evaluate contacts in a true sense, because this can now be done from a computer. So I just want to emphasize that this is not necessarily to replace mapping at the face, but to complement it so that we can better use our time and not hold up production. And again, so these meshes serve as a permanent record of what is seen. So what's involved in the actual process? This is the equipment that we used up at Fenelon. So on the right is just the camera. On the left is our light source. So we used 2 bar LED lights that we would hook up with tripods and then use jumpstart batteries to use as a power source. This would give us about 20 minutes of light, which was more than enough for a mapping routine. Kind of by the end of the bulk sample, we were doing it in about 10 minutes to take all the photographs we needed. For the process itself, we would do it in teams of 2. So we'd set up the lights first in order to get an even lighting across the face. Then one person would proceed to take photographs of the face and the walls in the back. The second worker would then still produce a more standard geologic map, but just quickly getting the contacts and not spending that time trying to get them exactly right. So once the pictures of the face were completed, the second person would then start collecting chip samples as part of our grade control routine, while the photographer would then start taking pictures of the walls in the back. So for the process, we'd take photos from several vantage points, first focusing on the face, then on the walls. And one thing we realized is that it was really important to get good photographs of the corners as well for the stitching process. From each of these points, we'd take several photos angled at different orientations to cover the entirety of the wall, and we're looking at about a minimum of 30% coverage just for the stitching process again. So not shown here, we would then later take pictures of the back in order to complete the mesh. So in total, we'd take about 70 to 100 photos, and like I said, this would take about 10 minutes. So once back at surface, we would use a third-party software called Reality Capture. And this would bring all of the photographs together and then stitch them into these 3D meshes. So the 2 photos here are from one of the drifts that we developed during the bulk sample. So initially, what the program would do is form a cluster of data points that have the colors applied from the photos. And then once you're satisfied with how this looks, you can use the software to render this into a 3D shape. So On the right-hand side is a fully formed mesh that has the color from the photographs applied to it. And as you can see, this looks kind of like what you would see in reality. So at this point, what we have is a 3D shape with no spatial information. So the next step is to georeference this into 3D. This was a pretty easy process as well. So what we would do is just paint 2 rock bolts on either side of the drift. And then we'd have a surveyor come in and take survey measurements for each of these points. We'd put this right into reality capture, and then this would georeference the map in the software itself, and we have a fully 3D spaced mesh. At this point, it is fully ready to be brought into Leapfrog, and so what you can see right here is that a line of these meshes brought in and how they compare to a drift outline taken through a standard surveying technique. So you can already see that this lines up exactly with the standard surveying, but what you're also getting is a more detailed outline of the drift itself. So I'm going to switch gears a little bit, give a bit of a background and overview of the Fenelon deposit, and then show some of what you can do with the technology. So the Fenelon gold deposit is located up in northern Quebec, like I said. It's along the Sunday Lake Deformation Zone, so this is similar east-west trending and deep-seated structure to the Cadillac Lauder Lake, which hosts the Malartic deposit and the Macassa deposit, as well as the Porcupine Dester, which hosts many of the deposits in Timmins. So up on the Sunday Lake, we also have the Detour Lake deposit, so a multi-million ounce deposit. And as being Archean greenstone hosted gold deposits, these are quite structurally complex, several stages of deformation as well as several stages of mineralization. So understanding these deposits is already quite a challenge. Kind of zooming into our area, so this is the Fenelon deposit itself. For the bulk sample, we focused on mineralization in the main gabbro body. And this was all that was known whenever we acquired the project in 2016. Since then, though, we've discovered an entirely new mineralization to the southwest, and we're starting to get really excited to potentially go after this underground as well and continue to implement photogrammetry as a way to help understand the mineralization going on in this portion of the property. So I'm not going to talk too much about that. I'm going to focus really on the bulk sample that we completed, where we were looking at these high strain shear zones with localized mineralization. Which I think I have a better example in the next slide. So this is kind of a simplified geology model of the main gabbro deposit with the underground development that has been done set in with it. So what we have are these parallel anastomosing shear zones with high-grade mineralized chutes within them. The 2 that we went after for the bulk sample were the Naga Viper in red and then the Chipotle in green. If you can see, they're all named after hot peppers. So these were quite a structurally complex, and because of the anastomosing nature and how closely spaced these are, one of the problems that we commonly encountered based on drill data was, do these link up the way we think they do in 3D space? This is a stylized cross-section through the main gabbro deposit again, showing just kind of some of the complicated nature and features that we would see of the mineralization. On the right is just the development that's been done on the project. So in brown is everything from pre-Wallbridge. It was first open pit in early 2000s, and then on previous bulk sample in 2004, developed the first 2 mining levels. We came in, and in 2018 and 2019, we put in another 5 levels of mining and produced the ore through long hole stoping. So I just kind of want to draw attention to the NVO3 stope. So this is our highest grade stope, and it was about 4,500 tons at 38 grams. So this is just kind of showing the high grade mineralization that is present on the deposit. Because who doesn't like to look at a bit of core? So this is our mineralized zones. What we have are these strongly silicified shear zones with abundant sulfide mineralization. One interesting feature of the deposit is that we do have quite a bit of chalcopyrite. And other than gold, this is our strongest proxy for mineralization. This also lends itself quite well to photogrammetry, as it's a feature that's quite visible in these 3D meshes, and it contrasts the geology around it. So it makes it much easier to outline these ore zones. So the reason we decided to use photogrammetry at the Fenelon bulk sample was because we really wanted to understand the geology better. What you can see here is just what was a very quick sketch of the face, just showing the main contacts. And then down below is one of these meshes that is fully referenced in 3D. You're able to rotate this around to get better angles and then determine the geologic contacts directly from there. So we saw this as a really good opportunity to kind of test this new technology and see how it works for us. And one of the things that, or some of the features that we found that were quite beneficial is that this lended itself extremely well to modeling the mineralized zones in the geology. It was also extremely useful to go back and reinterpret the geology or learn new things that we just didn't have time to really see when looking at the face. We can also then visualize all of this information in 3D with other data collected through drill holes and through sampling, and then do 3D structural model, or not modeling, but collection of data directly in Leapfrog as well. And then we use this to help refine our stope shapes as well as plan for breakage and dilution. So this map's a little bit more detailed than the previous one. But again, this would take maybe 10 minutes to collect the face. So instead what we did was we dedicated that same amount of time to collect the photographs, and then we could do that more detailed modeling directly on the meshes from a computer. Again, I just want to emphasize, especially after taking the SRK course yesterday, this is not meant to replace geologic mapping at the face, because you can still collect quite a bit of important data that you won't really be able to see from the computer. But it's a good way to complement it so that the geologists can dedicate their time more efficiently at the face for the data that really needs to be collected. Because even when you're producing one of these kind of maps, you're never going to get the contacts exactly right by eye unless you're dedicating a significant amount of time. Whereas because these are also georeferenced, by just drawing that line in 3D on the mesh, you have your exact contact drawn out. So this kind of leads into the next slide. So what we would do is we would use the polyline feature on Leapfrog to directly trace out our contacts. Sometimes we'd actually still bring in our face maps where we had a bit of difficulty seeing where these geologic contacts might be. And this would help during the process quite a bit as well. And so with Leapfrog, again, these polylines can then be directly imported into your model to influence the orientations that you see there as well. So again, instead of doing this on maps and then trying to bring the same information back into Leapfrog, you do it all at once. So it's quite a time-efficient method as well. So on data integration, so this picture on the right, what we've done is displayed the meshes on 2 different mining levels, and then we're looking at all the assay data that we collected through other means. So kind of down in this area, you see a few of the drill holes that are coming through. Radiating up from the lower drift are our test hole samples. On each level are our chip samples, and then test hole samples going out the side. So then we're able to actually look at how these assays relate to the geology features and the mineralization. So previously, this wouldn't even really be possible because by the time you have your assay results back from a lab, that next round's already been taken and you've lost that information. So this on its own is, again, quite a valuable tool where you can go back, review your geology, and compare that to your assays. And then so stepping a little bit further, so we would use these to help influence the model that we use to outline our mineralization. So this is shown in red. And then finally, after we would take our stopes, we used CMSs and brought those in to compare how the actual stope broke. And then we could look at the fracture sets that may have had an influence on where the edges of the stopes were breaking. So you can do quite a bit of reconciliation and geotechnical work from these meshes as well. So kind of jumping over to the structural side. So in our deposit, so we had a lot of magnetic localized anomalies, and as such, trying to collect structural data underground with the compass was not really possible. This is generally a difficulty with the ground support that's going to be metallic and affecting the readings as well. But again, all of this can be done directly in 3D from Leapfrog using their structural disk tools. So in this example here, what we've done is we're measuring some of the angles that we would see from the shearing. So we'd use the face and the back in order to get a true 3D orientation of these planes. And what you can already see is that there are several orientations even in this one face. Through Leapfrog, again, we could immediately visualize all this data on a stereo net and then start trying to interpret what the shear zone is doing. Kind of stepping further from this, we're also able to look at this from drift to drift and different locations in the mine. And so for this, you can start looking at the variability of some of these structures and start also reassessing whether the initial models make sense. So what we've done for this is we've created a mesh simply from the structural planes and then see how it links it up naturally in Leapfrog and kind of look at that and say, does that make geologic sense? If it doesn't, what do I need to do in order to make it fit better? And so again, in our case with these parallel zones, We actually reinterpreted partway through the project how they connected, and photogrammetry was a huge help for that. Another kind of feature of this too is you can start looking at how you can expect the rocks to break, and then start planning more effective dilution and, unplanned dilution, and just what you can expect from the stopes. So before I go to the summary, I'm just going to read a quote from Richard Knight's paper that I think fits quite well. So it's production mine geology must be accurate and efficient in order to reduce risk and ensure that ore value and mining operations revenues are maximized. And really, photogrammetry does an excellent job at covering both of these features. So for our system, it was maybe $1,000 to $1,500 worth of equipment, and we don't spend any more time at the face than a standard mapping procedure. So we're both being quite time efficient as well as cost efficient for the collection of this data. And I'm just going to once again highlight the last point. So what I really see as the most useful result of this kind of data collection is this unbiased record of the rounds. Because we all know that as we collect a map, that's a simplification of the geology, and it's not true to what's actually there, and inherently it has to be. But also, it's going to be biased by the geologist that's collecting that data. So from this, you can actually relook at this, and as interpretations of the formation of the deposit change or just the understanding of the geology, you're no longer locked into that previous bias. You can kind of reevaluate everything from scratch, looking at the geology itself. And that is everything for me. Thank you for your attention.